Welcome back, Night Owls. This is Dr. Nighttime. And tonight we're continuing along with my LTAM course. We're continuing along with Chapter 5, Annuities. As I mentioned, Chapter 5 is broken down, or I'm breaking down Chapter 5 into two sections. This is Section 2. Section 1 covers the basics of annuities and some of the basic arrangements you can have. This section includes a couple of formulas that more complicated formulas that allow for more detailed calculations. If you haven't seen Part 1 yet, I highly recommend you go back and watch that one first, as this section will presume competence and full knowledge of the notation introduced in Section 1, and some of the steps of algebra that were explained there won't be explained here, because I'll assume that you've gone through that enough, both on reading, looking through Section 1, watching the video on Section 1, and going through the recommended homework for Section 1. So, there are a few big formulas here. I talk about the Annuity-Insurance Equation, Woolhouse's approximation, and the Uniform Distribution of Deaths approximation. First up, I'll begin with some more notation. If you see big A super M, that means payment is made at the end of the period of death with M periods per year. So, for example, if M is 12, that means payment is made at the end of the month. Right. So this would be payment is made at the end of the month of death. Little a double dot M means it's an annual or monthly or monthly payment. It's payment of size 1 over M, made every month or however big the period is. Notice that this means little a double dot super M should be on the same order of magnitude as just a double dot. Because instead of getting a payment of 1 at the beginning of the year, it's just spread out over the course of the year. So it's going to be slightly smaller, but same order of magnitude. And in the limit as M goes to infinity, you'll have continuous insurance and continuous annuities. You just denote that with a bar over the big A for insurance and little a for annuities. There's actually an equation relating annuity values to corresponding insurance values. Let Z be the present value random variable of a $1 per year annuity to an X-year-old. So that's little z. Right? Let big Z be the present value random variable of a $1 life insurance for an X-year-old. So, if you remember Curtate notation, right, K sub X, meaning the number of whole years until the person dies, little z equals 1 over 1 plus I plus 1 over 1 plus I squared, etc., plus 1 over 1 plus I to the k sub x. We do our geometric series line dance, right? Divide by 1 plus I, take the difference. You get z times 1 minus 1 over 1 plus I equals 1 minus 1 over 1 plus I to the power k plus 1. And this right here, this is big Z, right? It's a payment of 1, and you discount it not by the amount of time until the beginning of the year of death, right? You can't make a payment at the beginning of the year of death because you don't know that it's the beginning of the year of death when it happens. You have to make the payments at the end of the year of death. So you get Z times 1 minus 1 over 1 plus I equals 1 minus big Z. So little z equals 1 minus big Z over 1 minus 1 over 1 plus I. And this 1 minus 1 over 1 plus I, you might recognize that as the discount rate, D. And that's the shorthand I'll be using, D for discount rate. So we find that the present value random variable for an annuity is 1 minus present value random variable for insurance divided by D, assuming it's fully discrete for a whole year. And if I want to get little a double dot and big A, that's just going to be expectation of little z and expectation of big Z. So we get little a double dot equals 1 minus big A over D, just from taking the expectation of both sides. And this formula you'll be seeing again and again and again and again and again. Often you'll need both little a double dot and big A, and they'll only give you one of them, so you can use this to get the other, assuming you know what the discount rate is. So, as an example, right, if we just sanity check this, show that the values of big A50 and the values for big A50 and for a whole life annuity for a 50-year-old, as printed in the SULT, satisfy the annuity insurance equation. So we just look it up. So we look up the values from the table. Little a double dot 50 equals 17.0245. Big A50 as printed is 0.18391. And so if we take 1 minus big A50 over 1 minus 1 over 1.05, we crunch the numbers in, we do get 17.0245. So we verified the result from the table. And one case where this relationship comes up as rather important is variance of the value of an annuity. Right? If you were paying attention, you might have realized, okay, if we want variance for an insurance value, we can do squared AX minus AX quantity squared. For A double dot, they give us A double dot, they don't give us squared A double dot. But that's okay. If we use the annuity insurance equation to find the variance of the value of a $1 per year whole life insurance paid to a 50-year-old, well, again, if we let little z be the present value random variable of the annuity and big Z be the present value random variable of the insurance, again, I can't call it little a and big A because those are averages, and variance of an average is just 0. It's an average. But the individual random variables themselves have some variance. So I can say variance of little z for the annuity equals variance of 1 minus big Z over D. And if you remember your properties of variances, you can break this down. Just do the algebra here. Adding this constant doesn't change the variance. Making something negative doesn't change the variance, right? If it was higher, now it's going to be lower because you made it negative. Dividing by a constant divides the variance by the square of that constant. So we get variance of z equals 1 over d squared, variance of big Z. And now you can look up squared A50 minus A50 quantity squared. Crunch our numbers together, and we get the variance of the annuity value for a 50-year-old is 6.72. So whenever you have to find variance of an annuity, you want to use the annuity insurance equation. Find the variance of the appropriate insurance. And find the variance of the annuity that way. Alright, so what if we need to modify for term annuities or immediate annuities? So, for a term annuity, little a double dot x colon angle n, I actually can say that this is just 1 minus big A x colon angle n all over D. Why? because so the best way, one way to think about relating A double dot to big A is to imagine a cataclysmic event that's certainly going to kill somebody in n years, if that person isn't already dead. For the annuity case, that means that payments will stop after n years. For the insurance case, that means if payment hasn't already been made, it will be made in n years. So if we kind of force Q sub n to be 100%, we say, follow whatever mortality assumption you had up until then, and then we know the person's going to die then we get this relationship here. So we can't just say little a double dot x colon angle n equals 1 minus big A x colon angle n over d. Where, again, d equals 1 minus 1 over 1 plus I. For immediate annuities, we'll just say little a sub x equals 1 minus big A sub x over d minus 1, right? Because we'll just say little a sub x equals little a double dot sub x minus 1. If you remember from part 1, there we had that formula relating immediate annuities to annuities due. And so we're just making that adjustment here. And of course, if it's a term immediate annuity, then we compare that to the corresponding term annuity due, subtract 1 for the payment at the start, and add the endowment for the probability of there being a payment at the end, right? If you were to compare annuity policies, one of which is payable at the beginning of the year and one is at the end of the year, as the calendar rolls over, as long as you survive that New Year's party, you get the payment, with the only differences being at the very beginning, one of them gets you a payment and the other doesn't. And at the very end, one of them gets you a payment only as long as you survive, and the other never gets you a payment. So that's where these two correction terms come in. Now, suppose you modify the compounding period. So now the payment is of size, the periodic payment is of size 1 over m. And it's just, as we do our geometric series line dance, we are not dividing by the full 1 plus I, we're dividing by 1 plus I to the 1 over m. So we can pretend that our year is only 1/nth of a year. Our insurance rate is, sorry, no, our interest rate, rather. Our interest rate is 1 plus I to the power 1 over m. And then instead of saying 1 minus 1 over I to the, it's 1 minus 1 over 1 plus actual insurance, we say 1 minus 1 over modified insurance rate. And so we can say A double dot x super m equals 1 minus big A sub x super m over d super m, where again, d super m is defined as it's the monthly discount rate. So it's m times 1 minus 1 over 1 plus I to the 1 over m. Hopefully you remember that from exam FM. And to go continuous with this, you just take the limit as m goes to infinity. And in the limit of continuous increments, just your discount rate will just become the force of discount, which is also the force of interest, just this delta. So we'll say a bar sub x, little a bar sub x equals 1 minus big A bar sub x over delta. All right, so could go through some examples of that, but again, it's just those same couple of formulas. The next big idea is Woolhouse's approximation. Now, when I introduced Woolhouse's approximation for survival as kind of that supplement to the Chapter 2 video, I said that we'd be bringing it up again around here, so here I am bringing it up again. And this is usually where it gets introduced. As you may recall, Woolhouse's formula relates sums to integrals. So, if we wanted to try to relate a bar sub x to a double dot sub x, well, alright, so a double dot sub x is clearly a sum, right? It's a sum of expected present values of payments. And so the continuous version of that would be an integral. Now, when we think present values of payments, well, what function would we be summing? You'd need to survive, and you'd have to account for interest or discount. Which means it's actually going to be a sum of endowment figures. So a double dot sub x is the sum of endowments. A bar sub x is the integral of the endowment function. So, as an example, suppose we want to use the three-term Woolhouse approximation and the standard ultimate life table to estimate a bar sub 50. Now, three-term Woolhouse approximation involves a derivative. So you will need some estimate for the derivative of TE50. And yeah, and so what I would do is I would actually use the definition that XE50 or I guess TE50 is L of 50 plus T divided by L of 50. Divide that by 1 plus I to the power of T. And so what I did is I actually calculated the appropriate value for a 49-year-old and a 51-year-old. And did a symmetric difference quotient there. You could do other interpolations, right? You could just compare 50 to 51 and say that's close enough to a derivative. But what you can say in this example is that a bar x is approximately a double dot x minus 1/2 plus 1/12 the derivative with respect to time of TEX when t is 0. If you remember that from the three-term Woolhouse approximation. If not, I suggest you re-watch the video on it from the supplementary video to Chapter 2. So, the integral of some function is approximately the sum minus 1/2 plus 1/12 the derivatives at the endpoints. Now, one thing I'll add in. Typically, you'd have to say derivative as t equals 0 and compare that to, and subtract from that derivative when t is infinity. But as t goes to infinity, TEX goes to 0 smoothly and horizontally because you have a small survival probability and there's interest, right? So for large values of t, TEX is going to go to 0, and so increasing that, it's still going to be just about 0. So the derivative will also be 0. So that's why I don't have to subtract that out. And so then I can approximate TEX by comparing number of survivors and multiplying by the appropriate interest or discount factor, that'll get me 1EX and negative 1EX. I want a symmetric difference quotient. Though, you might feel like negative 1EX is just a weird thing to use, so you might just compare it to 0EX, and that's totally fine. It's a matter of personal preference. And in fact, you know 0EX is just going to get you 1, so it's a little shorter to do it that way. I just went for slightly more precision. I divided by 2 because I estimated the derivative with rise over run, and because I'm comparing 49-year-old to 51-year-old, that's a difference of 2 years. So the run in my rise over run has to be 2. So crunch all these numbers out, and you get that A bar 50 is approximately 16.52. Note that's roughly 1/2 less than A double dot 50, at the 17.0245. That's to be expected. What if we wanted whole life insurance? Well, so remember how with variance we said, okay, we can easily get variance of an insurance and use the annuity insurance formula to get variance of an annuity? Now we do it the opposite way. We can use the Woolhouse approximation, right, to get continuous annuities. A continuous annuity is an integral. Woolhouse approximation relates an integral to a sum. Discrete annuity, which we have in the table, is a sum, so I can get the value for the sum from the table. I can use Woolhouse's approximation to get the value of the continuous annuity. Then you use the annuity insurance formula to get the value of the insurance on its own. And you get big A50 is approximately 0.194. Okay. This delta value, by the way, you could either do by taking 1 minus 1 over 1.05 directly, or, as I'll show, so going forward a little bit, because I was going to have something on here. Anyway, in the limit as m goes to infinity, d sub m, notice page 6 of your tables. If you turn to page 6 of the tables, you'll see a chart like this. Okay, so I rounded it to 0.0488. They have 0.04879. But that's where you can get it from. All right, and you'll notice that this is slightly greater than the 18931 that they have printed in the table. You could also estimate it by saying, well, whenever death happens, it will happen approximately 6 years in advance. Sorry, 6 months. So payment will be accelerated by about 6 months, right? Instead of waiting until the end of the year. So you could just say, yeah, I'll take my 0.1893 and multiply by square root of 1.05. And you should get something pretty close to this. Anyway. So that's how it works for a whole life annuity. What about a term annuity? Well, if you remember, when you set up your Woolhouse staircase, you'd have to worry about what happens at the far end of the staircase. If your staircase goes infinite, you know that NEX goes to 0, and it goes to 0 with slope 0 as time goes deep on into the future. For a term annuity, we can't take advantage of that. So we need the full version. We need to say, if I go back to the picture of my Woolhouse staircase, if I'm stopping over here, then the areas of these triangles I'm cutting off are base of 1 and combined heights of 1, that's going to be 0EX, minus NEX. So I have 1/2 base times height. The base is 1. The height is going to be this difference. And then similarly, for the next order term, I need 1/12 of derivative at t equals 0 minus derivative at t equals n. If you don't remember where the 1/12 comes from, go back to the Chapter 2 video where I discuss it there. It comes from cubic splining. And I walk through the derivation there. So, if we want to use the 3-term Woolhouse approximation and the standard ultimate life table to approximate A bar 50 : angle 20, so for the continuous term annuity, we find that A bar 50 : angle 20 is approximately A double dot 50 : angle 20 minus 1/2 of 1 minus this difference in 1 minus this endowment figure plus 1/12 times this difference in derivatives of the endowment figure. I crunch all our numbers in. These are looked up in the table. I showed you how I calculated this on a previous example. This one gets calculated a similar way. And I get that A bar 50 : angle 20 is around 12.5145. Now, most of the time, when they ask about Woolhouse's formula on the LTAM, they're actually not going to ask you to compare a fully discrete annuity to a fully continuous annuity. They'll ask you to compare a fully discrete annuity to another discrete annuity with a faster compounding period. And so if I wanted to compare the continuous annuity to the discrete annuities, right? If I compound m times per year, the second term for the triangles, that's going to be smaller by a factor of m. Because if I look at 1/2 base times height for these triangles, the combined heights will still be the same. They'll go from here down to here. But the bases will only go 1/mth as much. So you divide the second term by a factor of m. And for the third term, that ends up being smaller by a factor of m squared because not only are, when you're looking at your difference, not only is it going over 1/mth the width, but also the derivative itself, when you differentiate with respect to time in terms of your compounding period, right? If you were to set up the cubic spline and just readjust and say, I'm going to rescale my distance so that here to here is 1, so that I can set up my same spline and get the 1/12. Now your derivative is 1/12 of what it was before, because you're essentially stretching it out. Or sorry, 1 over m squared. Or sorry, 1 over m of what it was before, because you're stretching it out by a factor of m horizontally. So you have to account for that, plus the fact that you're looking at a smaller region. So you divide by m twice. So as an example, for a monthly term annuity, suppose we want to use the 3-term Woolhouse approximation and the standard ultimate life table to approximate A double dot super 12, so monthly, 50 : angle 20. If we use the same derivatives that we used before, what we'll notice, on the one hand, we'll say A double dot super m is approximately A bar x : angle n plus 1 over 2m times the difference in, or times 1 minus endowment minus 1 over 12m squared times derivative with respect to time of endowment at the beginning minus endowment at the end, or derivative of endowment at the end, right? So we do that. Then, if we don't want the super m's, we just don't have the m's down here. We're setting m equals 1. And since both of these have the continuous version in them, we can just substitute directly in. And when we crunch our numbers together, we get this formula. A double dot super m x colon angle n is approximately a double dot x colon angle n minus m minus 1 over 2m, right? It's going to be this minus 1/2 plus 1 over 2m. 1/2 is m over 2m, so we get m minus 1 over 2m. Times this term, that's the same throughout. And then similarly, we have plus 1/12 minus 1 over 12m squared. So this becomes plus m squared minus 1 over 12m squared. And again, times the difference in derivatives. Anyway. Next, suppose we had to deal with end-of-month insurance rather than end-of-month annuities. So if we had to use the results of the previous example to find the actuarial present value of a 20-year-old endowment insurance, or a 20-year endowment insurance on a 50-year-old, well, we know that a super 12 50 colon angle 20 is 1 minus d super 12 a double dot super 12 50 colon angle 20, right? We can just say, use the annuity insurance formula. And so we get that it's 0.3893. The last condition you have to worry about is if you're given a survival function and an interest rate. So that means you don't just use a table, right? They don't say, here, use this table. So if you're given a table or some annual values, then sure, you'll just look those up. If you're given a survival function and an interest rate, okay, so we can find the endowment figure. That's not a problem. In fact, you might even want something they could ask you to do. So they give you a survival function and an interest rate and say, first calculate the continuous annuity, right? Because now you set up an integral. Okay, you can do that. If you need to set up, if you need to find an annual, right? So now you need to find a sum given an integral. So now you need to use Woolhouse's formula. And to use the third term of Woolhouse's formula, you need to find the derivative of NEX, right? Because Woolhouse's formula calls for a derivative. And to do that, so we know TEX equals TPX times e to the negative delta t. Differentiate. And so when we're differentiating, we have to use product rule, right? Because both of these depend on t. Here, it's just we just multiply by delta. Right? As we're differentiating e to the negative delta t. So we multiply by negative delta, rather. Here, we need the derivative of TPX. And the derivative of TPX is just negative force of mortality times itself. So, at t equals 0, the derivative is just going to be negative mu x minus delta. And at times infinity, it's going to get you a 0. You may notice, if you look at page 6 of the LTAM tables, their version of Woolhouse's formula is for whole lives, and it has a mu x plus delta in it. That's because you subtract 1/12 of the, you subtract 1/12 of the derivative. So these minuses become pluses and they get divided by 12. But often they'll want you to use it for term annuities, and I find it's really easy to think you can just use this formula from the table when you can't. That formula is only for whole life annuities. Whereas I found it's really helpful to think of Woolhouse's formula as a way of relating sums to integrals, and then if you have to relate two sums with different compounding periods, you relate both of them to the integral and use the integral as a go-between. So one last thing. Uniform distribution of deaths approximation. You may recall that a sub x super m is I over I super m a sub x. If we use the annuity insurance formula, a lot of algebra happens. I actually won't walk you through the entire derivation unless somebody specifically requests it in the comments. But you'll eventually get a double dot sub x super m equals some function that depends only on m times a super x minus some other function of m. These alpha m and beta m's are called interest functions, and you can find them on page 6 of your tables. If you look for common values of m, they give you the values. If they give you a weird value of m, like 3, say it's 3 times a year, you can use these right here. While I typically recommend understanding the derivations of where most of these formulas come from, this is one that I wouldn't necessarily recommend. I'd say, yeah, it's safe to just have this bottom line there, just because you need to start with this, and you remember how weird it was to get this to begin with. Then use the annuity insurance formula. Okay, that's not so bad. But then all the algebra that, I mean, if you're ultimately getting something that has I times d over I to the m d to the m, and then I minus I to the m, that's going to be a bit of a mess. So with that, sorry, I had an example here. So use the standard ultimate life table and page 6 of the tables to estimate a double dot super 12 50 colon angle 20 using UDD approximation. We just crunch our numbers in, and we get that it's approximately 12.5412. Notice before, using Woolhouse approximation, we got 12.5416. Why is one a little bit bigger than the other? So uniform distribution of deaths assumes that the deaths are a little more spread out. Whereas Woolhouse's approximation will actually figure out, it'll use that curvature to figure out, or to try to estimate, are more people dying earlier in the year or later in the year? And over the age range 50 to 70, mortality is increasing, so you'll get more deaths later in the year. Which means, using a uniform distribution of deaths, you'll assume slightly more pessimistic survival. And more pessimistic survival means lower value. Again, it's hardly a difference. It shows up in the fourth decimal place after the decimal point. But that's why one is slightly smaller. Anyway, with that, this concludes the content and the information loading for Chapter 5. For homework, I recommend doing the remaining problems from Chapter 5 from the SOA official problem list. I'll be uploading a video with those solutions shortly. And as always, if you like the way I explain things and want to arrange private lessons, click the link in the description below. And until next time, this is Dr. Nighttime wishing you a good night.